In this lecture, we'll be dealing with periodic properties. And the title slide gives an example of a periodic table based on Mendeleev's periodic law. And it kind of shows you different ways that the periodicity of the elements can be displayed. And we'll go through some of them in this class. Right. The first part of the lecture, we're going to be reviewing periodic trends. So hopefully you remember most of these. Things like effective nuclear charge, atomic size, ionization energy, electron affinity, electronegativity. These are all things that have periodic trends with respect to the periodic table. Okay. And then we'll introduce some new concepts, and those are the uniqueness principle, diagonal effect, inert pair effect, and we'll talk a little bit about that metal, non-metal line. Okay, and so this stuff was hopefully expressed in and covered in the supplemental reading, the second supplemental reading for the course. Okay. So Dalton's periodic table, Dalton, sort of the one that first came up with the idea, the modern scientist to come up with the idea of atoms and the atomic nature of matter. He had his own sort of list of elements. You can call it a periodic table, I suppose. And it was almost like an alchemist's list, right? They had symbols for all the atoms, and I think a lot of those symbols might have been drawn from alchemists. Okay. Well, we really consider the father of the modern periodic table and this idea of chemical periodicity to be Dmitri Mendeleev. And his table is shown here. Okay. He grouped elements, the known elements, at least the known elements to him, into 8 groups. And you can see some of them here. A lot of them are following the columns that they're in the periodic table. Okay. And many of them are in the same group that he made. They're in the same group or column they are now today. Okay, you'll see some elements that are different outside the group. If you look in group 7, fluorine, chlorine, bromine are all halogens, but he also has manganese in there too. So remarkably, for his time, 1871, he was able to get pretty close to what we know the periodic table to be today based on valence electrons. Okay. This is a modern periodic table. I made these slides in 2018, so that's kind of where this is from, but I don't think anything major has changed since then. And again, how we have the periodic table grouped and organized is based on, the groups are based on valence electron configuration, right? In this group, you're all 1s valence electrons. These are all 2s. And you have 1p, 2p, 3p, 4p, 5p, and 6p. Okay, and then the d electrons would be in the transition metals. And then the F electrons are in the inner transition metals, the lanthanides and actinides. We can make a long form of the periodic table where we would actually put the lanthanides and actinides in between the S block and the D block. So this would be actually a more accurate picture. We just don't do it because it takes a lot more length to do that, primarily. I think another reason is because these lanthanides and actinides, we just, they're not very commonly used in everyday sort of chemistry. So moving those down to the bottom, it saves space, and those, the amount of people that need to access information about those is much smaller than the other elements. Periodic law is the observation that there's repetition of physical and chemical properties in elements. Okay, so things like the alkali metals will react with water very violently to displace H2. So that was noticed, right? And so that whole family, you could kind of match them together and group them together just based on that observation, how they reacted with water. And we know now today that's because they have that same valence electron configuration where that electron is very easy to get removed, okay, and actually reduce hydrogen gas from water. And then halogens, they all react with metals to form ionic halides, okay, and that again is because they have that electron configuration where they really want to gain an electron to get a noble gas configuration, so they react with these metals to form halides. We're going to talk about certain properties and periodicities. They all seem to really stem from effective nuclear charge. And so what effective nuclear charge is the number of protons an atom has minus the number of inner electrons. Or I suppose you could think of that as core electrons. Okay, so the number of protons minus the number of inner electrons. So those inner electrons effectively shield some of that nuclear charge to the outer or valence electrons. And that's what the Z effective is. Okay. And the general trend of Z, the effective nuclear charge, is that it increases as you go from left to right in the periodic table, and it increases up a group. So in that sense, helium would have a very high effective nuclear charge. And one of the reasons is that it doesn't have inner electrons, right? Remember the trend in size of atoms? This will follow the opposite trend of effective nuclear charge. So as you go down a group, atoms get bigger. As you go from left to right, atoms will get smaller. So the opposite trend, going from right to left, the atoms will get bigger. Right? So it's the opposite of effective nuclear charge. And when you think about that, the higher the effective nuclear charge, the tighter that atom's going to hold on to its electrons. It's going to hold them closer, and it makes that atom smaller. So the smaller the effective nuclear charge, the less likely or the less tightly it will hold the electrons, and the atoms will be bigger. And the opposite, the higher the effective nuclear charge, that atom's going to hold on to the electrons tighter, and it will be smaller. That holds true, except remember the lanthanide contraction. Right, we talked about this. This is kind of a reason why those transition metals, when we drop from, if we drop from the 5th row to the 6th row here, in the transition metals, we don't get really any size change, a drastic size change, because it's just the lanthanide contraction limits the the effective nuclear charge, in a sense, is higher because these F electrons don't shield as well. Right. Here's another slide demonstrating that lanthanide contraction. So for the main group elements, this trend holds as you're going down groups. The size continues to increase. But again, when you look at that third and fourth row of the transition metals, I should say second row and third row of the transition metals, there isn't an increase in size from those two. Okay. Okay. Ionization energy. Ionization energy follows the trend that just in general, it goes from gets higher as you go from left to right, and in general as you go down a group. But you see, if we just walk through the second row here, remember there are certain places where there's a step down, right? And so the addition of one p electron to boron, there's a step down now because that one p electron is much easier to remove than that s electron when it's in a full subshell in beryllium. Then we go up to nitrogen, and again there's another step down to oxygen, and that's because 3p electrons is a half-filled subshell, which is fairly stable. So removing one of those is harder than removing a fourth electron from the p orbital. Okay. But in general, it increases as you go from left to right. And again, remember that trend in transition metals, it doesn't really increase very much. In general, it's increasing as you go from left to right, but only very, very slowly, right? And primarily, mostly at the end, the last one, because those are filled d orbitals. So most of these have very similar ionization energies. This is a graphic way to represent ionization energy. Okay, as you go across a group, in general, it goes up. Then you start the next group, it's way lower, and you're moving across, in general, going up. And then here we see the transition elements, when they come in, they are much flatter, right? It's not this drastic increase across that row, that period. It's a very gradual increase. The metallic behavior trends, it follows the same trend as atomic size. And one of the reasons for that is it's based on that effective nuclear charge again. The less tightly an atom's holding on to that electron, the more easy it will be to lose that electron. And that's really a metallic behavior, is being able to lose electrons, give up electrons. Okay, so first review question, explain the relationship between Z effect, effective Z, ionization energy, and metallic character. Well, hopefully we've done a good job of that in this lecture. Right. So let's first look at the ionization energy. So for a higher, as your effective nuclear charge gets higher, so does the amount of energy it takes to remove an electron, the ionization energy, that will also get higher. So a higher effective nuclear charge will lead to a higher ionization energy. So they are directly proportional. And as effective nuclear charge gets higher, the opposite happens with metallic character, right? Metallic elements will tend to lose their electrons and have positive charges, right? Higher nuclear charge, effective nuclear charge, makes that more difficult to lose the electrons. So if you have a higher Z effective, you'll have there'll be lower metallic character in those elements. And vice versa. A lower effective nuclear charge will lead to higher metallic character. Right. The other trend is electronegativity, and this one is a big deal in chemical bonding. Unfortunately, there's not a huge trend that is always followed, but in general, elements will get higher as you go from left to right and from the bottom of a group up to the top. So that's sort of in general. If you're comparing elements in the same row, you're good with that. If you're comparing elements in the same group, you're pretty good with that trend. But comparing two elements in different rows or different groups, especially different rows, it would become a little bit more challenging there. You can see for the transition metals, and this is one trend I don't think we really talked about, but they're all relatively low electronegativity values, which we would expect because, again, they're metals. There are some exceptions. Those exceptions are shown here. Probably don't really need to know these though for this class. And that brings into the effect of the metal-non-metal line. Okay? So when we talk about metallic character, effective nuclear charge, there comes a point where the effective nuclear charge becomes high enough that the element switches from being more metallic-like to more non-metal-like. And that happens at this line. And on many periodic tables, it's highlighted, or the elements on either side of the line are sort of highlighted a different color. Okay, and we mentioned this in a previous lecture, right? And these orangey shaded elements here are referred to as metalloids. So they're kind of have characteristics of both metals and non-metals. Right, and that's one reason they're used in semiconductor production. That brings us. So we've discussed the overall review of the periodic trends from hopefully you covered in the first quarter of general chemistry. Now we're going to go into some new principles. One is the uniqueness principle. Okay, so for the uniqueness principle, this is the idea that the chemistry of second period elements is significant from their conjugators, or the elements that are in the same group. And that is the other kind of idea to this is that the third period element in each group is a kind of a better representation. Okay, so what's that mean? That means the second row of the periodic table, so things like oxygen, fluorine, neon, those aren't necessarily, and I guess for the noble gases, it would be helium is what we'd be talking about for that one. Those are not necessarily the best examples of the chemistry of the group as a whole. And if you take the next one in line, so the third row for most elements, for most groups, like sulfur or chlorine, that would be a better representation. Okay, so there are three reasons for the different reactivity among second period elements. One is the small size. They are generally much smaller than the rest of the elements in the group. 2, enhanced ability to form pi bonds, and 3, unavailability of d orbitals. Okay, so quantum mechanically, if they're in the second row, n is going to be equal to 2, and so they can't, quantum mechanically, they cannot have d orbitals, right? L, if n is 2, L can only be 0 or 1, so an s orbital or a p orbital. Right? And because of their enhanced, their small size, they don't have d electrons, d orbitals. That's kind of what gives them this enhanced ability to form pi bonds. So in general, these elements are the ones we're going to be talking about when we refer to the uniqueness principle. Now, if we look at the reasoning here, if you look at this size, in terms of size, these second row elements are all pretty much much smaller, especially when you get into the nonmetals. They're much smaller than the rest of the elements in their group. Right, and again, that's showing in this figure another way of looking at it. This is with electron affinities to be lower than predicted by the effective nuclear charge, and that's due to electron repulsion. Right. The other aspect of the small size is the ability to form pi bonds. The small size increases the degree of the covalent character. The atoms can approach each other closer. They can the orbitals can overlap more, and right, the likelihood of overlapping in those p orbitals increases, and that's what forms the pi bond. If the two orbitals are larger, the overlap is not as likely, and that's why, for bigger elements, you don't see the pi bonding that you do in the smaller ones. Right, so for silicon, right, for carbon and silicon, they're in that same family. And life on the planet, on our planet, is carbon-based, so some people think that life could also be silicon-based, but it's much harder for silicon to make these pi orbitals, and you just don't see them, at least in the conditions here on this planet. So the number of different types of bonding available to silicon is much less than with carbon, even though they have the same valence electron configuration. And then that lack of access to d orbitals. Again, this is quantum mechanically forbidden for these elements up here. So period 3 and greater have access to those d orbitals quantum mechanically, even though in period 3 they don't actually have d electrons. They still have access to those orbitals. And an example of this is in oxygen, right? Oxygen can only form tetrahedral compounds. It only can be hybridized as sp3. Sulfur can have expanded valence and have up to 6 fluorines or other atoms bonded to it, because it can access d atomic orbitals and hybridize to sp3d2. And that's what was known as expanded valence, in that anything kind of third row and down can undergo expanded valence, and it thus have an expanded octet. Right. If you want to think about hybridization again, right, these figures from the book, kind of explain that. You're mixing 4 atomic orbitals, an s and 3 p's, to get 4 equivalent sp3 hybrid orbitals. But if you have access now to the d orbitals, you can expand that valence even further, and that's how sulfur can get to sp3d2. Whereas oxygen just doesn't have these because quantum mechanically it can't. Right. Phosphorus, same way. You can have a PCl5, that compound, that's an expanded valence. And again, it's reaching into the d orbital to do that. Okay. The next principle we'll talk about is the diagonal effect. Okay. And that's where an element in one group can be similar to an element in the next group over and down one. So you move over a group and down one, so on a diagonal, and they share some similarities to each other. So lithium and magnesium would share some characteristics, beryllium, aluminum, boron, silicon. Okay, so there's this diagonal relationship between first member of a group and a second member of the next group, specifically. 3 reasons for this. There's going to have similar radii. Remember that atomic size will decrease as you go from left to right, but also increase as you go down. So if you go one step right, you're going to be decreasing in the next group, but if you also go one step down, you'll increase from there. So these will have similar size. Okay, you'll have a similar nuclear charge to radius, effective nuclear charge to radius, atomic radius ratio, and they'll also have similar electronegativity. Right, and so the electronegativities here are shown. For lithium, it's 1. For magnesium, it's 1.2. For beryllium, it's 1.5. Aluminum is 1.5. Boron's 2. And silicon's 1.8. So those are similar. And then you'll see that the atomic radii are pretty similar, and also the charge density. Okay, so this is from figure 9 in the book. Excuse me, 9.15, in chapter 9, figure 15. Okay, it's important to remember that the group relationships are stronger than this diagonal relationship. That's another thing to point out here, that the group that it's in is far more important in terms of chemistry than this diagonal relationship. Right, so some things that come from the diagonal effect: structures of gaseous and solid beryllium chloride and aluminum chloride. So they share this diagonal relationship with each other, and you can see that they form similar structures when they are bonded to chlorine, right? Both can sort of get this networked tetrahedral sort of bonding with like a chain of aluminum or beryllium and chlorine atoms. Right, so the next property or principle we'll talk about is the inert pair effect. Okay, so the inert pair effect states that the valence s2 electron pair and s2 electron pair of metallic elements, particularly those of 5s2 and 6s2 pairs that follow the second and third row transition metals, are less reactive than we would expect based on trends of effective nuclear charge, atomic size, and ionization energy. So what does that mean? That means, so we're in 5 and 6s2 pairs. Those s electrons in these elements are less reactive than we would expect. And remember that, excuse me, things like lithium and sodium, they react very violently in water, and that trend is followed, but those electrons are less reactive in the rubidium and cesium. Yeah, so this really is taking effect in the transition element range. And because of this inert pair effect, things like tin or lead, antimony, bismuth, they don't always show their maximum oxidation states. And the compounds formed with an oxidized state 2 less than expected group valence. Okay, so these are just 2 electrons that are not given up as easy as would be expected. Okay. The thought that the cause of this inert pair effect, one of the reasons is that lanthanide contraction. Okay, in those 2 rows, you get the lanthanide contraction where those electrons aren't being shielded as much anymore as they were in the row above, in the transition elements above. Okay, so 4s, 5s, and 6s electrons of, where are we, Ga, In, and Tl are not shielded as effectively from the nucleus by the intervening D and F subshells. Okay, that means, in a sense, the orbitals are more porous, and that's what leads to that lanthanide contraction. Okay. So those elements that we mentioned in terms of the inert pair effect have a higher ionization energy than predicted because they're not being shielded as much, and the effective nuclear charge is higher than would be predicted. Right, so this gives higher than expected ionization energies. So an example of this, lead that's in group 4A, typically loses 2 electrons when ionized rather than 4. Okay, so where's lead? Where are you? Are you even shown in this figure? There we are. Right, so lead here would typically, it's in that same group as carbon. Typically, for this one, you would think, okay, it can be a maximum of 4+ charge, but it typically only goes to 2+. Right, so in summary, periodic law is the repetition of elemental physical and chemical properties. Okay, we have discussed those periodic trends that we reviewed from the first quarter of general chemistry, and those were things like atomic size, ionization energy, and metallic character, electronegativity, and they're all based on and can be explained on effective nuclear charge. Okay. Some other new principles we talked about, the uniqueness principle, and that was the second period elements are going to be significantly different from their elements further down their groups. The diagonal effect, there's a strong diagonal relationship between the first member of a group and the second member of the next group. And that's because their sizes are similar, their effective charges are similar, their electronegativities are similar, so they show some similarities there. Okay, and then again, the inert pair effect, That's elements to the right of the second and third row transition metals. So there'd be the, I think I misspoke earlier, saying that it's the transition metals. It's not. It's the main group metals that are to the right of those second and third row transition metals. Okay. They are less reactive than expected, and that's because of that. They have that higher effective nuclear charge than would be expected because of the poor shielding from the F and D electrons. Okay, and then finally we talked about that metal-nonmetal line, and that's the division of the periodic table into metals and nonmetals, and gives the metalloid region. So the elements that kind of border that line, all except aluminum, are considered to be metalloids. All right, so let's try some review questions with these principles. And these are, fairly simple questions. Okay, oxygen forms OF2, but sulfur, selenium, tellurium form hexafluorides. Explain this observation. Which concept from this lecture does this illustrate? Right? So this is, oxygen would be that first element in that group. And then these other elements are all elements below it in the group. And remember, oxygen's also in the second row. So this would be illustrating that uniqueness principle. Unlike phosphorus, arsenic, and antimony, bismuth does not form a pentachloride. Explain this observation. Which concept from this lecture does this illustrate? All right, so you have to look at the periodic table. You see that phosphorus, arsenic, antimony, and bismuth, they're all in the same group. Bismuth is one of those that's far enough down, though, now that the inert pair comes into effect. So it's less reactive than we'd expect. So this would be the inert pair effect. And then finally, what is the main reason that elements in the same group have similar reactivity? So hopefully, this is the question that I hope everyone could answer. Why do elements in the same group or column have the same reactivity or similar reactivity? And that's all due based on their valence electron configuration. Right. That's why they are in those groups. We're grouping them based on valence electron configuration. And valence electrons are what's responsible for chemistry.